Hey guys, this is Carrie, and this is the answer key for homework number 4. So we're going to solve each of the following equations. We have x squared is equal to 64. To eliminate x squared, we take the square root of both sides. We get x equals 8. Now, one thing we haven't been that careful about in class recently is because we have x squared equals 64, we should be getting two solutions here. So you should also get the solution x equals negative 8. And so in class, I guess we made the decision to be less careful about this, just to really focus in on this inverse operation aspect. But we really should remember that whenever we have a power of 2, you get two different solutions. For the next problem, we've got 2 to the x equals 128. And it looks very similar, but instead of trying to get rid of an exponent to isolate x, we're trying to eliminate a base to isolate x. So to eliminate the base, we're going to use logarithm base 2 and logarithm base 2 on both sides. So when we do log base 2 to this side, that gives us x by itself, because the base canceled out, equals log base 2 of 128. This gives us x equals, and to put this in the calculator, we do log of 128 divided by log of 2. This gives us x equals, and so let's see, log of 128 divided by log of 2. Let me use my calculator over here. You get x equals 7. Next up, determine the value of each of the following variables in each of the following equations. So I'll do a couple of these, but I think you can figure them out. So maybe I'll just do one. 13 to the 8th power equals 28561. To solve for a, we need to eliminate the base. So we'll do log base 13 to both sides of the equation. Log base 13 and base 13 cancel out. This gives us a equals log base 13 of 28561. To plug this in on our calculator, we do log of the number we're taking the log of divided by log of the base. And we get that a is equal to, let's do this on the calculator, log 28561 divided by log 13. That gives us a equals 4. So I'm going to leave the next two for you because I think that you can figure them out based on the work we've done. For problem number 3, it's really similar. We want to end up with something that looks like a number to a power equals another number. So to do that, we need to get rid of this 2 first. To get rid of the 2, we divide by 2 on both sides. We get 25 to the x power equals, I don't know, let's see, wow, 7, 8, 1, 2, 5, I'm hoping. And then we do, let's see. To get x by itself, we need to cancel out base 25, so we'll do log base 25 on both sides. This gives us, and I'll know if I got the other problem wrong, if I get a horrible answer here, but log 25th, 7, 8, 1, 2, 5. Now we'll put this on our calculator. We get x is equal to, let's see, log 7, 8, 1, 2, 5 divided by log 25. X is equal to 3.5, so that looks pretty good. Nice. All right, for problem number 4, I'm going to leave this one for you to solve on your own. For problem number 5, we start to work with an interesting idea, which is, in the past problems, we saw that to kill a base, use log. In this problem, what we're going to see is that to kill a log, use the opposite, a base. And this is a pattern that you've seen a lot of times in math. The same way plus and minus and plus, to cancel out addition, you use subtraction. To cancel out subtraction, use addition. You can always use two inverse functions to cancel each other out, vice versa. So let's see. This time, we're starting off with a log. So we have the log base 5 of x equals 3. To cancel out a log, we know that logs usually are used to cancel bases, so to cancel a log, we use base 5 on both sides. Base 5 and log cancel out. This gives us x equals base 5 to the 3rd power. X is equal to 125. For problem B here, we've got log base 4, 3x minus 5 equals 2. So in order to cancel out this log here, we need to use a base. So you do base 4 on both sides. Bases and logs cancel out. That gives us 3x minus 5 equals 4. base 4 to the second. 3x minus 5 equals 16. 3x is equal to 21. X is equal to 7. Great. I think you can figure out problem C on your own. For problem 6, there's a typo in this problem. Sorry about that. It should have said 10x instead of 16x, I hope. All right, let's see if I fix the problem. So this one looks a little bit crazy. We've got log base x plus 3, a 10x plus 30 equals 2. We know to get rid of a log, we use a base. So let's do base x plus 3 to this side and base x plus 3 to this side. Bases and logs cancel out. They're inverse functions, so that gives us 10x plus 30 equals, and now we've got all of x plus 3 as a base raised to the second power. So actually, I think I should, let me just see if I can do this. I'm going to take this and move it over so that it looks a little better. Great. So you x plus 3 to the second power. Let's see, 10x plus 30 equals x plus 3 to the second power means that thing times itself. 10x plus 30 is equal to x squared plus 3x plus 3x plus 9. 10x plus 30 is equal to x squared plus 9x, or plus 6x, oh my gosh, plus 6x plus 9. Now we subtract 10x on both sides, we subtract 30 on both sides, because I'd like to use factoring to finish this problem, and I need it to be equal to 0. That leaves us with x squared minus 4x minus 21 equals 0. Next up, we get x minus 7 times x plus 3. Pause for a second. What factoring method did I just use? If you said sum and product, you're right, because we're looking for two numbers that sum to -4 and have a product of -21, and these do it. So it looks like for our final answers, we get x equals 7 and x equals -3. So these are two possible answers for our question here. And I guess, just kind of making this a challenge problem. One thing we haven't talked about yet is for logs, it's possible to have positive numbers as the bases. It's possible to have decimals as the bases as long as they're positive. But one thing that's not possible is we aren't allowed to have negative numbers or 0 as bases for logarithms. See, there is no such thing as log base 0. That doesn't exist. And there's no such thing as log base -4. That doesn't exist. So technically here, I've got two answers, and I need to check to see if any of them are extraneous, if any of them are fake. So I'm going to plug 7 back in to check it. So let's see. I get log base 10 of 100 equals 2. And if you use your calculator, this does work. If we check x equals -3, we get log base -3 plus 3 is 0. And then we get of 0 equals 2. And what we just said down here is there is no such thing as log base 0. That doesn't exist. So this function is actually, this solution is actually an extraneous solution. It doesn't actually count. And we get only one solution, x equals 7. So there's a lot of mathematics in this problem that I think was possible to figure out based on what we had seen in class today. All of this, even getting the two solutions. But in order to get the final answer, you had to know some extra facts, is that there is no such thing as log base 0 and no such thing as logs of negative numbers, or log base negative numbers. All right, guys, I'll see you in class tomorrow. Hope this was helpful. Bye.